the Are You Here quizzes for now. I'm thinking of kind of trying to incentivize following the lecture more than I had been. So if we do switch to more substantive quizzes and possibly to quizzes that are just in person, I made a scheme. Then like the scheme would be like one of the questions is like what's on the board and something like that. Because I feel like so for the lectures, I know they're recorded, it's kind of fine. For you know, for labs, people haven't been going, which is really weird to me because that's like free marks in the lab and also free marks on the midterm if you learn the material in the labs. So it's, you know, okay, all right. I have a DM. Okay, I'll check it later. So hi. Hi, new people. Do the quiz, please. People do see the quiz, right? Yeah, okay. So, all right. So, for implementing classes in Python. So to remind people, classes in Python work kind of like structs in C, but they have functions. So those are called methods that are built into them. So I'll just quickly do the example from yesterday again. So we have a class student. So in C, oh, that's 6. So it's so class student, and then so let me save it as a Python file so that it can get highlighting. That. So init is a special function that gets called with the student being created, and it has necessarily one argument that's the thing that's being created. I'll show it in a second again. And then we'll have ESC190 mark. And here, so this is just from yesterday. And here we initialize it like that, right? So we say self.name is name, self ESC190 mark is ESC190 mark. And then you can create a student like so. So this would be Jack gets sent to this name, and the 98 gets sent to ESC190 mark. And then the student that's being created, that's the self, that's the first argument. So in effect, you're saying something like s.name is Jack, and something like I do the quiz, and s ESC190 mark is equal to 98. All right. So that's what happens when you use the name of the class. So it's as if you're using init as a function and you're getting the object back. All right. Okay. So the convenient thing, again, is that you can have functions that are associated with the object. So you could say, for example, you know, print self.name and ESC190 mark. And what it allows you to do is to say s.print. And that's the same as saying student.print and then s. So student.print is this function, right? So you're calling this function and you're giving it s, and s, the s.name was set to Jack, s.ESC190 mark was set to 98. Right, so that would print Jack 98. Right, so it's a way of kind of combining the attributes of an object, so the name, the mark, and functions that operate on those attributes. So, for example, the print does that. All right. So what I want to do now is I want to create a class like that would work like a stack, right? So what does it mean? So if you remember, this is what we need from the stack. So we need a push, we need a pop, and we need an is empty. So we could implement it. We did implement it yesterday, in fact. It was just like stack push, stack pop, and so on. So now I want to implement it as a class where the data, the elements would be stored inside the class, and then the functions push and pop and is empty are going to be associated with that particular data. So let's do that. So I'm going to say class, and I'm going to call it stack. I'll again save it as a Python file. So I'll define an init. So in this case, for the student, I sent in the name and the mark. Here, I don't want to really send anything. I want it to be the case that when the stack is created, it's just empty. So what I'll do is I'll say self stack is equal to empty. So that way, when I create a stack, so to create it without any elements, you do need the empty. Now as.stack is the empty list because we set it to that. Make sense? So now what I want to do is I want to say, okay, I need an is empty. And that'll return self stack equals to, or I guess length self stack equals to 0, right? So that's going to return true. If it's equal to 0, it's going to return false otherwise. And I want to push. So push can just be append to the stack that I'm now storing inside the capital S stack, right? So I'll say self stack append element. And I want to pop. And that would just be a pop. So here I might like to say, okay, like what's going to happen if the stack is empty? No, so if the stack is empty, then what's going to happen? Well, in this case, it's just going to crash, right? If you try to pop from a list, just a Python list, and it doesn't have any elements, that's just going to crash the program. And you might say, well, that's what you get. Similarly to how you might do error checking the way we did with string, you can first say, okay, like I'll be nice about it and I'll just print a warning or something instead of crashing, right? So I'll say if self is empty, I also do like this. So this is kind of a very primitive way of handling this. So Python actually has something called exceptions, which we won't do this year. But there is kind of like a more uniform mechanism of dealing with those kinds of things that's not just printing stuff. But that would do as kind of a demonstration. So, all right. So that's kind of like that. So you can say as.stack, and in Python, basically in other languages, there's sometimes there's restrictions. In Python, there is no restriction on trying to just say, as.stack.append directly. You can do it if you want. It's just that you're bypassing those mechanisms that you built in, but you can do it. So you can, as.stack is actually legal, but to try it, you would say something like whatever. So as.push. And whatever 52 as the push 150 125, and then we can try to print the stack here. So again, no problem with just accessing the stack if you want to, and we can do like as.pop. We can print that, So what would it be? So it's like 52, then 125 is on top. So the stack would just be, 52, 125. So pop would print 125. And then if you print the stack afterwards, it just has 52, right? So that's like this. So s.pop, I neglected to say return here, which is why it said none. But if I say return, so we started out with the stack 52 and 25. Then we display it over here. Then we say s.pop. So this returned the 125. So this 125 got printed. And then what's left in the stack? Well, 52. Does that make sense? Questions? All right. So like we mentioned last time, this is not necessarily that efficient. So Python lists are not exactly array lists, but close enough. So Python lists store the elements in sequence. In fact, for the people complaining, why ever do I need triple pointers? We don't say triple pointers. Why do we need pointers to pointers to pointers? Well, the list in Python, it's actually a quite sophisticated thing, right? Because it's not a block of integers. It's not just integers. The list can be heterogeneous. So it necessarily actually stores pointers to every object in the list, right? So this innocent looking s.stack is actually a block of pointers to Python objects. Therefore, if you were to store it in C, what you would store is the pointer to the pointer that's the first in this list. And if you were to want to send it to a function and modify it, it would have to be a pointer to that, which would be a pointer to a pointer to a pointer, just like in last year's midterm, although I believe not this year's midterm. Okay. So those things actually matter sometimes. Okay, all right. So with that said, so list to a first approximation is like the array list that we implemented in Python, in that the pointers, yes, there are pointers, but they're stored contiguously one after the other. And then sometimes you run out of space and you need to move the whole thing to a new location. That happens. Okay, so that means that append potentially is all that. And the reason for that is, so you have your block of pointers and you want to put one more at the end. It might be that there is no space at the end. So that means that you might need to realloc essentially. And realloc potentially moves the entire self stack somewhere else in memory. Does that make sense? Does that not make sense? Questions? All right. So this is all then. Pop is actually all one. So like again, like in the lab, actually one of the variants was you shrink the block of memory if you can sometimes. So potentially it's like more than O of one if you really want to save on memory, but like to a first approximation, it can be O of one. This cannot be anything other than O of n because the list does store things contiguously. At some point, if there's just no space in the current block of memory where you're storing your stuff, you got to move everything out elsewhere, right? So it must be O of n in the worst case. Like usually kind of here, the worst case is different from the average case. Like usually it's probably fine. So, okay. This as well is O of one. So that was our motivation for making a linked list, where with a linked list, you would not have this O of n behavior. So we are about to embark on that. I'll make a quick note saying that you might well ask, okay, like, okay, fine. Like in order to do a stack with an of one push, you need a linked list, but you never told me why I would ever need a stack in the first place. Seems useless. You should be thinking that because it should seem pretty useless right now. By the end of the course, I will have at least one, hopefully two examples where a stack is actually quite useful. But for now, yes, it's an abstraction. It's this thing where you can push and pop, and it shouldn't seem like it's an extremely useful thing. So okay, but it is like it makes your computer work to the extent that it does. Okay. So all right. So my goal now for the rest of the half hour is to implement a linked list class in Python and then use it to implement a stack with O1 push and pop. All right. And kind of part of the goal here always is, like, yeah, like somebody's implemented already, of course, but like we're also learning Python along the way. Yes.
Before we go ahead and build it, how can you tell us how, like, why we might think we'd be able to even do this, or then push it all around?
I kind of did yesterday, but we can go back to that. All right, flick. So the idea would be that we have our linked list. So something like this. And what we're able to do with the linked list is we're able to insert at position 0 at O of 1, and we're also able to delete at position 0 with O of 1. So the way you would insert is you would make a new, this is delete, right? So this is an example of an insert. So you just say, well, I mean, I would not replace the head. I would replace the thing that's after the head. But yeah.
Sure. Okay.
Right. So
it's kind of like stored backwards.
Right. So basically inserting it. So kind of to finish the thought. So inserting is all one, because if you know where you want to insert, in this case, you want to insert at the head. All you need to do is you need to create this new node and say, well, so it used to be that this next was hooked up to this node. So instead I'll do kind of surgery on the linked list and I'll say, okay, next here is going to be to this new node, and next from the new node is going to be to the old thing at index 3. So that's all one, because all you need to do is rearrange those connections. Deleting, so if you want to delete, for example, the thing at index 0, what do you need to do? Well, you just need to say, first, the arrow used to point here, and now the arrow would point here. So that's also all one. Yeah.
How come iterating through the linked list is not considered during the runtime?
So so the question is, how come iterating through the linked list is not considered during the computation of the runtime complexity? And the answer is it is. So it's just that we say that if we don't need to iterate, meaning if we know the location where we want to insert or where we want to delete, then you don't need to find that location. And in this particular case, as promised yesterday, we do know how to do that, because we just want to always insert and delete at the head. Right? So, all right. Okay, but first, we'll implementing just a generic linked list. So I'll do a class LL and the init. It'll look like this. So I'm going to say self dot So it's just gonna have a head, and initially it's gonna be none. So again, kind of the init, it's not exactly the definition of the structure, but it's kind of similar visually, right? So like a linked list had a head kind of in the examples recently. So here we're just saying self.head, initially it's going to be none, and then we can update it, right? So we want an insert. So that's going to be self and location and element. So we'll define that later, because right now we also need to define a node. So that's, again, kind of very similar to the examples from before. So here, you just say self.data equals data. So one thing to note is that init is not special, right? So we're saying self.head equals none, and it might seem like we just made up head as an attribute. We never said anything about it before. And in fact, that's exactly what's going on. So so with Python, you can do it, right? Oh, well. So I can have anything. I can have a list. And then I can say L.head is now an attribute. Oh, list is not actually allowing that. So I'll make it a function instead. So I'll do like so f is a function, doesn't do anything, but it is a function, and I can say f.head is equal to 5, and now f.head is equal to 5. You can do it with so list, as it happens, I got unlucky and list disallows that, but by default, Python objects just allow that. You can just say, I want f.head to be something. It says, fine. Like now f.head is like any other variable. So that is, I don't necessarily recommend thinking this way, but under the hood, that's what's going on. Is over here, we're just saying there's now such a thing as self.head. Self.head is this object that's being created right now. And now that init has run, there is such a thing as self.head happens to be equal to none. Like that's the mechanics of it. So, all right. So similarly here, I'm saying self.data. Well, now self.data exists. Didn't before. And then we'll say, okay, so self.next initially is going to be none. Right. So now I can do something like n is node, whatever, 52. So now n.data is 52, and n.next is none. Right. So again, I think the way to intuitively grasp it is to just say it's just like a struct, and I'm initializing a struct. In actual fact, what's happening is that the init gets called, and inside the init, Python says, okay, line 17, self.data equals data. Amazing, now we have a self.data. Right, and it didn't have to be inside init, so you can say like n what that, well, not that, but and this is equal to 12. That's fine as well. Now this particular n has this attribute. All right. So okay. So now that we have a node, we can do an insert. So how to do an insert? I'll make a little picture. So we have like head, and then we have n0, we have n1, and so on. So that's our linked list. So to do the insert, what I got to do is I got to walk from the head, and I gotta walk log times, right? And then I'll insert after I walked through this linked list this many times. So I'll take care of the special case first. So I'll say if log is equal to 0, then that means that we're inserting right at the head of the list. So that means we're saying, let me create the node first. So new node now has data as element, and next is none currently, so just the default value. So if location is equal to 0, I just need to replace head with new node. And before I do that, I need to remember to make new node connect to head next. Right? So the order here is important because this is self-head. So the order here is important because if I overwrite self.head, then I don't have self.head.next anymore. So first I say new node is coming on here. So this is going to be n. And I want new node to be hooked up to n0. And then I'll just replace head with n. So it's going to be like this. Is that making sense? Questions? So a word about kind of the pointers here. So in Python, you see that this is easier, and it's easier because you have fewer options, right? So there is no such thing as an arrow and everything. So in a way, like you lose the ability to go to an arbitrary address in memory and try to change it using the star operator, which is what the arrow does. But on the other hand, everything easy because the only option you have is like on the left-hand side, it's whatever, like Python variables. On the right-hand side, it's Python variables. That's the only thing that's possible. So sometimes that makes it so that you cannot do what you want to do, but what you can do is much easier, right? So here, self-head next is the address of, so everything in Python is an address, right? So here we're saying copy the address from here to the address here. Here we say copy the address of new node to self-head. Yeah.
For how we get to the first element, don't you want a point that's the current head, but not the next node?
So head is like a special thing, right? So head is the pointer. Sorry. So head is like the address of the first node. Oh yeah. So self-head. Yeah. Thank you. Yeah. So new node next is self-head. Yeah. Thank you. Yeah.
So
yeah. So I kind of was inserting after the head, not before. Sorry. Thank you.
In this case, is the top of our stack is the head.
And we don't have a stack anymore yet, right? So we're just making a linked list. So okay. So that's insert. So that's if location is 0. If it's not 0, we just need to iterate. So I'll say current is self-head. And then I'll say for I in range lock, current is current next. And now that I'm done, so I stepped current times. So now what I want to do is, so I'm here. So this would be, so I started with head, then n1 and so on, and I have my n. So if I want to insert at index 2, for example, that would mean that I'm inserting over here. So I want current next to be this, and I want this next to be current next. Right? So if current is N1 and current next is N2, so two things. I want N next to be N2. N2 is currently current next. And I want current next to then be the new node. So, okay. So I'll say new node next is current next. And I'll say current next is new node. Make sense? So again, and like you've done it a little bit in the lab as well, but what you do is you draw a picture, right? So we said, I want to insert, so I'll just reiterate what I said. So I want to insert N. This is what things look like. I want to insert N after index 1, for example. So if I want to do it after index 1, I want to step once. So I want current to become N1. And then I want to say N next is N2, N2 is N1 next. So that's the reason for this line. Right? So new node next is current next. So N next is N1 next. And then I want to say current next, it used to be N2, but I want it to be N. So I say current next is equal to new node. Yeah. So head is kind of the first one. So like the math there is correct. So like if location is 0, we don't step at all. If location is 1, so we want the new one to be 1, so we step once and then we insert. Yeah.
You know dot next is equal to the one after current dot next.
Or no. So if current is right. So if current is in 1, then we want N next to be N1 next. Sorry, to your question, yes. So I was again kind of inserting after the location. Actually, I want to insert before. So yes, location -1. So that's just kind of a matter of semantics. So like if I want to insert 1, then yes, like I would say I want to insert just after head. So all right. So that's insert. So delete would be like this. So we are deleting at location lock. So what do we want to do? So let's say that we are in this situation. So we have head, we have N1 and so on, and then N2. And let's say we want to delete at location 2. So what we want to do is we want to walk again location -1 times. Thank you. So because if you want to delete N1, we actually want to walk. So we want to walk location -1 times because if you want to delete N1, you want to be at head. If you want to delete N2, you want to be at N1. And that's because when you're deleting N2, what you want to do is you want to say N1 next is N2 next. So you want to have access to N1, right? So if we're deleting N2, we want to get just to N1. So, okay. So again, we'll say, so if location is 0, all we need to do is just self head is self head next. And that's it. So like if you want to delete the head, all you need to do is just say N1 is the new head. In Python, you don't need to free, because in Python, if there is a node that's not referenced anywhere, it would be automatically freed for you at some point. Yeah. Yeah, you had a question?
Well,
Okay. Yeah. All right. So that's like that. Otherwise, we walk -1 times. So here we'll say, okay, so current is equal to self head. And here we're saying current is current next. And now current so how do you delete? Well, you just say, okay, so I want to delete current next essentially. So we'll say current next is equal to current dot next dot next. Right? So that way current next is going to be skipped. Right? Because so if you're thinking about I want to delete N2, well, how do you do it? Well, just say N1 next is now N3. So next time you go through the list, N2 is going to be skipped. All right, so that's delete. To review kind of the syntax side of it. So self here is just used as the stand-in for the object that you are working on, right? So if the object is the linked list, it basically has one variable that's the head. And anytime we're inside functions that operate on the linked list, we send the self there so that we can update the head for the particular linked list that we are working on. So that's why you have self every time that you mention head. Does that make sense? So because it's like the head of the particular linked list that we're thinking of. Everything else is just what you're used to from the last months in C applies to Python. It's just simpler in the sense that everything is basically a pointer. Right? So in the context of C, what you would have is head is node star and head next is node star and so on. And current, you would define node star current. Like everything would be a pointer. And just like in the Python code, you could then say, for example, current is equal to current next. Right? So that's the C code that's equivalent basically to what we're doing in Python. The difference is that in C, you have other options sometimes. In Python, there is no other options. Like everything is a something star, basically. So, all right. So that's insert and that's delete. So now that we have this, we can define our stack. So initially it's gonna be an empty stack. So by the way, for insert, so for an empty stack, what we need is to just call the linked list, right? So we'll say self.stack is equal to LL. So self.stack is now a linked list with head equals to null, to none. Right? And then the plan is push would be insert at 0, and pop would be get 0th element and then delete 0th element. Right? And you could do it at the end as well, the way we did it with list. It's just that it's more convenient to do it at the head. So that's what we'll do. So we'll have a push. So self stack insert. So insert takes location and it takes element. So it would be location 0 and element. I forgot the self here. So here, let's first get the head. So that would be self stack head. We'll then remove the head from the stack. So we delete the 0th element. And we return the value of current node dot data. And that's our stack with all of 1 push and all of 1 pop. All right, so I think it's kind of probably a lot of code all at once. Part of it is that you're not supposed to have to think about it all at once, right? So once we made the linked list, it's just a linked list, forget it. We're just now using it in a particular way inside the stack. So that's how I would first try to review it, right? So I would just say, okay, assume that the linked list works. Assume that you can do ll.insert and ll.delete. That's implemented somehow. Don't think about it. And then this is really easy, right? This is just saying, well, you insert at 0 when you want to push, and you get the data at 0 and then delete the 0th node when you want to pop. Right? So that's all stack does. Now, in order to know that this is all 1, we do need to know the implementation details of the linked list, right? So with the linked list, what do we do? Well, so the insert actually, like at location 0, is a special thing anyway. Here, by the way, it's so this is not going to happen anyways for location equals 0, so it doesn't have to be inside the else. But could put it inside the else, I suppose. This has to be inside the else. So we'll put all of that inside the else. So here what we're saying is will have nodes where node next is just the next node. And the way, for example, delete works is we update the head. Or if we're updating something other than the head, we first iterate through a list up until the node just before the one being deleted. And then we say, okay, if that was the connection before, we'll just make, for example, N1 next be N3. So the selves are kind of new. So all the self does is it just makes it so that you're able to use shorthand like this, right? Where you're saying node 52, and then inside of a init, the self is the node being created, so it can say self.data is equal to 52 without explicitly saying n.data is equal to 52. Or, like, so here, like, you're able to say, stack.head, and it just knows that you are referring to the particular stack that happens to be stored in self.stack here. So there's two selves there, right? So like there is the self for the stack, and there is the self for the for the linked list that has the head. All right. And this is a stack with O1 push and O1 pop. Amazing. So we'll do some practice next week in the lab. I'll see you. Bye. Whether there is a lab or not on Monday, I guess is like kind of in question. But I guess we'll find out. All right. Okay. I'll see you. Bye. So if there isn't a lab, there will be a handout, just possibly fewer TAs or no TAs. I don't know. So, yeah. Hey.
I do have the doctor. I don't know what's good.
We sent you an email about
Okay.
like your brand 7 out of 7.
Sorry, I don't really remember the email. So if you sent it, it's still in my mailbox. What's your name? Oh, okay.
We submitted the project and it ran past 7 out of 7 pieces.
Oh, I see. Yeah. Okay, I do remember that. Yeah, so I think what I said is I'll look into it. So I'll look into it.
Okay.
Yeah.
Okay,
Yeah. Yeah. Hi. Certainly. Yeah.